cost here.
Yeah, I know.
Okay. Hopefully this works, but all right. Well, okay, I won't waste any more time. Hello, welcome to Math Club, and welcome to my talk. Thank you. This is going to be called Ordinals and Slot Machines, Betting on Infinity. I will give a disclaimer. I'm only an undergrad, okay, so when I, right. So,
Silence, child.
you know, when I asked my advisor, like, do you think I'm in over my head talking about this topic? He just kind of laughed, and he's like, maybe, but we'll have fun anyway. So, he just said, you know, I'm going to be honest, right? I did a lot of research. I feel confident on what I have written. If you guys probe me for questions, I'll answer to the best of my ability, but I'm not going to lie to you. If I don't know something, like, I'm just going to leave you in the dust. So, you can ask me questions. I see the look on your face. You can grill me, but I'm going to invoke the fifth at a certain point. I'm going to not say anything. Aside from that, though, I'll get started. The good thing about this topic is you don't need a whole lot of math knowledge to kind of get into it. There's no calculus, nothing like that required. In fact, try not to leave in the first 10 minutes because it's going to start off really, really boring. Okay, I promise. For me, math people, this might be like super basic stuff. So, I'm first going to introduce the concept of a set. I know many of you have heard of this before. All we're going to do to describe what a set is, I guess in English words, you can think of it as a collection of objects. But in notation-wise, what we're going to do is we draw curly braces and we separate the elements with commas. So if I have the set of the numbers 1, 2, 3, it's just going to look like that. And a lot of what I want to kind of get you used to in this talk is how we compare sizes of sets and what happens when these guys get really large. We'll talk about that in a minute. But first, let me just mention, how do we actually compare sizes of sets? It's not a trick question. This is a very intuitive type of, I don't know, question, I guess. I reused that word twice. If I have the set of 1, 2, 3, I guess. If I have the set of 1, 2, 3, and I have the set of A, B, C, how do I know that they have the same amount of elements? Anyone on my math people can give me the accurate answer here.
Ooh.
Hazel, how do I know?
Well, what you could do is you could count the number of distinct elements and then match them up to each other.
Yes, I can match up the elements from both sets. So if A goes to 1, B goes to 2, and C goes to 3, I've matched everything up and I have the same size set in both scenarios. The fancy math term we use for this is a bijection. If that kind of tickles your brain for my math people, and you don't know what that is, it's a function that is injective, which means unique inputs get unique outputs, and it's onto, or surjective, so the size of the domain and the range are equal, so nothing gets left over. So now I want to extend this concept to infinite sets. This is again some kind of pop math stuff you'll see. But I kind of want to explore how this idea of a bijection can kind of break down, not really break down, but lead to some interesting results with infinite sets. So I'm going to start with the natural numbers, which, yes, 0 is an element. And I'm going to add these dots, just to kind of imply that this goes on. Yes, 0 is a natural number. People at home, it's a natural, I thought that's right. The dot, dot, dot implies that this goes on forever. And I'm going to introduce this new set. I kind of won't really name it anything, but call it E. And I'm going to use these elements. So these are clearly the even numbers. That's the pattern forming here. And I might ask, and I guess I'll pick on my non-math people in the audience, which one of these sets has a larger size? Anyone want to take a guess? Okay, can you justify that? You said they're the same because they're infinite, but I'm looking for something more. How can I use my notion of a bijection to describe the size of these sets? They are the same, I'll grant you that, yeah.
You can match them up.
Yeah, you can match everything up. I can do a perfect matching by just sending, well, I guess it's 1 or 2 the other way. 0 goes to 0, 1 goes to 2, 2 goes to 4, 3 goes to 6. Every single natural number gets its respective pair in the even numbers, and because this is a bijection, both these sets are the exact same size. So in an intuitive sense, I've taken these natural numbers, I've kind of removed half of the elements, but I can still form this bijection, and so they're the same size. And the way we write this is the cardinality is the fancy word, but I put these bars around n, and I would just draw e for my even numbers. So this just says the size of the evens and the naturals is the same. Everyone good so far? Okay. So now we'll introduce some other famous mathematical sets, and I'll ask the same types of questions. Z is famously the integers, so that's all of the negatives as well. All right. What might we think? Is the size of Z the same as the size of n? And I'll let my math people chime in if they want. Hazel.
I think they are.
They are? You're
And
correct.
in fact, I think using the evens will be really useful if you want to.
Yeah, essentially. And I know I don't, you know, I'm going to have to skip some of the more detailed bits to kind of keep this moving, but yes, I can find a way to match all of these values up to the set of naturals, right? You can already kind of think of a way that here's a set that is like half the size of this set. There's a bijection there. This set is like half the size of this set. So I can kind of find a way, like maybe all of the odd numbers, 0 goes to its guy, but then, 1, 3, 5 goes all the positives, and 2, 4, 6 go to all the negatives. There's a way to form a bijection here. So we can say that, yes, indeed, the integers have the same cardinality. Everyone comfortable with this idea so far? All right. I'll introduce another popular set. I'm going to keep it positive just for convenience. And instead of writing this all out in like a big list, this is just all rational numbers. So a rational number is a number that can be written as a fraction. So you can think of this as every possible fraction that you could ever write down. This one's more tricky. Do we think that q, or positive q, is the same size as n? Yeah, what do you think? You're saying no. Is there a reason why you think no? Oh, you didn't raise your hand. Oh, I'm so sorry. What do we think? Same size, q positive, same size as n? Yes or no? Yes, okay. And we can come up with a way to kind of map this out. One of the simpler visualizations of this is that if I kind of take a coordinate plane and I mark off each tick with, I don't know, natural numbers as you would expect, I could associate every single point on this plane with a fraction of, denominator with the x value and numerator with the y value. So like this fraction right here is 2/2. This guy here is, 1/3, or however I'm ordering it, but in a sense, every one of these dots on the plane gets a natural number. And the big idea I'm trying to describe here is the intuitive sense of what makes something equal to n. And the big concept here is if you can count them off distinctly one by one. So I could go from this guy to this guy to this guy to this guy, and you could sort of imagine as I move from each dot in this sort of spiral, I'm counting off the natural numbers, going 0, 1, 2, 3, 4, and kind of doing that process. And so the word we use to describe these types of sets, we call them countable, because that's what I just did. I just counted them off. All right. So now here's the kicker, which I went over this in a previous math club meeting, so some of you might be familiar with this. The big question is, are the real numbers countable? And that's the real line, of course. So I have, 0. I extend off in both directions. That's going to include all of the integers, all of the fractions, but also numbers that we can't necessarily represent as a fraction. So, pi will be out here somewhere. E will be up here somewhere. You know, square root of 2 is in here somewhere. Is this set the same size as the naturals? What do you think?
Any infinite set is going to be the same size as all other infinite sets.
Right, that's a good intuition, but I'm going to surprise you here, okay? They're actually not the same size. So, yeah, that's okay.
It's very sad.
And I'm going to show you a very nice visual proof for this. This is a very famous argument. It's called Cantor's diagonalization. Oh, you're going to see me not be able to spell diagonalization. Is that right?
Yes.
All right, Cantor's diagonalization proof. So what we're going to start by doing is assuming that there is a way that I can make this bijection. I do have a way to pair up all of my reals up to the, oh, sorry. I'm forgetting one very important step here. I want to make this a little easier on myself and use a subset of real numbers. And I want to actually find a way to convince you that the reals are the exact same as the interval from 0 to 1. If I find a bijection, I can do this. I'm going to keep this very short and sweet. If you really don't believe me that these guys are the same, look at the function arctangent. Right, am I thinking of the right one?
Yes.
Yes, I am, yeah. The function arctangent takes the real line and maps it onto 0 and 1. So at the very least, I know these guys are the same size. That's already a pretty weird thing to say. I'm actually telling you that, you know, this interval right here is the same size as every real number. But it gets even crazier, because even just this small little interval is larger than any of these sets I've already presented to you here. Okay, so back to my argument. I'm going to line up my natural numbers, and I'll make Dylan happy. I'll start with 1 in this case. But you can just sweep 0 under the rug for convenience. Okay, and then...
Sorry, you can't sweep in the road that you divide by. You put it like one shelf.
Yeah. So we're going to kind of assume that there is a bijection here. And I'm going to just give a random number between 0 and 1 to each of these natural numbers. So, I don't know, I'm not good at being a random number generator because I'm a human, but we can sort of just imagine a process by which we might assign numbers. And keep in mind, all of these guys extend off forever and forever. And what I'm going to do is I'm going to go to this number, and I'm going to look in the very first place, and I'm going to add 1, so I'm going to make it a 2. I'm going to look at this number, go to the second spot, and add a number. Well, this is a 9, so let's just cycle around and make it a 0, but it's still different. Third number in the third place becomes a 1. The fourth number in the fourth place, is that a 6 or a 0?
That's a 6.
That's a 6. There we go. Okay. I don't even know my own handwriting. All right. But what I'm doing here is I'm constructing a new number. And so this new number will follow every place that I named a new digit. So it'll be 2, 0, 1, 7, and it'll follow that rule and go on forever. And what I've actually done is I've created a number that is not in this listing. So I can ask myself, is this number going to be the number in spot 1? Well, no, it's different in the first digit. Is this number the same as number 2, or the same as the one in spot 2? No, it differs from the second place. Same as 3, differs from the third place. Any digit I try and claim that this guy might fit into, at that digit's place, and its decimal expansion is different. And so I've actually produced an entirely new number in my bijection. So this is not a bijection, actually. So what does this mean? Well, skipping over a few details, but take my word for it, is that the cardinality of all of these sets is actually strictly less than that of the real line. And so I want to pause and talk about what that means. We have 2 different sizes of infinity in the intuitive sense. And I've called all of these guys countable. and I'm gonna call this guy uncountable, because it wasn't any of those. And I'm gonna pivot directions kind of dramatically here, but I'm gonna leave this up, because what I'm gonna try and do for the rest of this talk is kind of shake you to your core at how, I don't know how to put that, just how large this uncountable set is, right? These are all infinite, and they're huge, right? These are, you know, whatever math YouTube video you watched that was like, here's Graham's number, or tree 3, or whatever. Okay, these are infinite, they all put those numbers to shame. But this uncountable realm, I need to put an adjective here, but this uncountable realm is so much larger than you might expect. And I'm gonna use gambling as a way to convince you of that. So, I'll pause. Anyone have a question about anything I presented so far? So I'm gonna erase and kind of start some new stuff. So, we're going good? Okay. Do you all know what a set is? Oh, so it's going away. All right. But again, I'll keep these guys up, and I'll even write something up in red to emphasize kind of the takeaway from this. There exists at least one uncountable set. So this is going to be my kind of backdrop for what I do now, because I'm going to change the pace a little bit. Okay, so there are two different sizes of infinity, kind of like there are, you know, there's just different infinities, well, there's different numbers. So I'm going to try and count to infinity now. I'm going to do this in a little bit of a weird way. So I want to start at the most basic sense. How do we build a natural number? I'm going to keep this short and sweet. The number 0 is going to be associated with a set of no elements. So there's nothing inside of it, right? And there's a special character for this. It's the empty set, but think of it like a basket with nothing in it. The number 1 is going to be a set, and I'm going to take the objects I have before me. So it's going to be the set of the empty set, right? So this is the number 1. And in general, if I have some number k, and I want to get the number k plus 1, I'm essentially going to the next number, looking at all the numbers that came before me and putting them into a big pile, and that's k plus 1. So the mathy definition of this is k join the set of k. Don't freak out too much if you don't understand this notation, that's okay. We can keep going a little bit, so 2 is the last one I draw out because it gets pretty egregious from here. I have this element which appeared here, this element which appeared here. So you can kind of think of 2 like the set of 0 and 1, right? That's all we're doing here. And this keeps going. So I keep going on and on and on and on. And at a certain point, I know I have to reach infinity, and so you can kind of imagine that this process ends with something on top of it. Now, before I write down what that object is, I actually want to try and justify to you that we actually can represent this. And the way we do this is through orderings. Without getting too crazy, we can compare natural numbers, right? We all know that 4 is less than 5. It's not very controversial. And we can say that 4 is less than 5 using this symbol. What's actually happening under the hood here in the most set theory sense is because 5 equals the set of 0, 1, 2, 3, 4, I can actually say that 4 is a member of 5. This symbol means that 4 belongs to 5. That's all we're doing there. But this symbol will do for this is what set theorists use. I'm not going to write this for numbers. It's kind of weird. Okay. Let's think about this example. here's the number 0, and I'm moving in this direction. Let's imagine a sequence. I'm going to start with 1/2. I'm going to jump to 3/4. I'm going to jump to 7/8, and then to, what's next, 15/16. And I can keep going and going and going. And if I follow this pattern, I'm always able to generate a next fraction in line, but they're gonna like approach this limit in essence. And I can always find a bigger value, but we still know that 1 stands on top, right? We can agree that 1 is on top of all of them. So in this ordering sense, I can say that, well, 1/2 is less than 3/4, just like I can say 4 is less than 5, but I know something sits on top, and this is gonna be our infinity. So I'm going to call this number omega, the Greek letter, and say that omega is the thing that sits on top of all the natural numbers. Are we okay with that so far? Okay. And in fact, we often correspond the cardinality of n with this number omega. It's kind of what, if you're reading a set theory paper, no one's going to say the natural numbers, they just go, oh, omega, right? That's how we think about it. Okay. I will pause again. Are we all okay on this idea of putting omega on top? The one thing I really want to point out here is omega, well, I'm going to pause. I'm going to give you one extra thing before I talk about omega in a sense. What might come next? So I want to be kind of like a smart ass. What comes after omega? Not nothing. There is something after it.
Omega sub 1?
You're doing a big jump. In cardinals, yes, but we're talking ordinals. Omega plus 1, right? That's all I'm doing. I'm taking omega, I got omega plus 1, and then I've got omega plus 2, and then omega plus 3, right? And I can keep going. And so you actually bring up a really good point, and I'll address that in a moment. Actually, I'll address it now, right? So the reason I said I was pivoting from what I talked about before, when I'm talking about infinity in this context, I'm talking about size. When I'm talking about infinity in this context, I'm talking about order. So this might not seem super intuitive at first, but all of these infinities, if I took them as a set, are actually the same size, right? It is true that omega is less than omega plus 1, because I can construct that using this definition, but size-wise, they're the same. I can find a bijection that associates them. And if you want to imagine omega kind of like a tower of numbers that approaches a limit, and then you can imagine omega plus 1 as this tower that approaches a limit, and then has an object on top of it. I can compare these using orderings, but a bijection can kind of cheat. A bijection can take this guy, send it all the way to the bottom, and it becomes indistinguishable from everything else. Are we okay with that? That's a bit of a tough thing to grasp sometimes. But all of these guys are all countable. They're all the same size, but they're still comparable. The next thing to differentiate with ordinals is there are 2 types of ordinals. There are successors and limits. There's also technically 0. 0 gets to be its own thing, right? So a successor ordinal simply says that I come after another ordinal at some point. All of the natural numbers you think of fit this definition, right? So 5 is 4 plus 1, right? That's a successor. Omega plus 1, or omega plus 2 equals omega plus 1 plus 1, right? But then we get limit ordinals, and omega is a limit ordinal. And what this guy means is that anything below it, right? If I take some natural number that's very, very large, right? I don't know what it is, like n, kind of somewhere in here. Anytime I take n plus 1, that's still strictly less than omega. I can always find something less than it in that hierarchy. Does that make sense? Are you okay with that idea? All right. So let's keep counting. We get omega plus 3. Eventually we get omega plus omega. Or in other words, we'll actually call this omega times 2. Another fun fact for my math people in the audience, addition and multiplication are not commutative with ordinals, and I can talk about that later if you want, but I'll leave that as it. You said that's gross?
Yeah, it's gross.
Right.
It's unhygienic.
Exactly, right? Oh, okay, to let you in on the joke, all I'm saying here is that this guy is not the same as this guy. It's different. Order matters here with infinite ordinals. Okay, well, let's keep counting. I can get omega times 3, omega times 4. I can keep going. I can get omega times omega, or omega squared. I can repeat this process more. I'm not done yet. We can go omega to the 3, omega to the 4, omega to the omega. Watch this. I can go omega to the omega to the omega to the omega to the omega. I can do this omega times, all right? It keeps going, okay? And I don't mean to surprise you, but this is still countable, okay? I'm not going to do a proof of that because I don't have infinite time either. But this guy and this guy, taken as a set, are the same size. Taken as orderings, they're different, but as sets, the same size. All okay so far? All right. But remember what I wrote in pink right here. There does exist at least one uncountable set. So I've got to have an uncountable ordinal somewhere. And what we'll kind of imagine is if we take every single countable ordinal and put them into one big list, at the very end, at some point after a long, long time, we get omega sub 1, which is what you mentioned. And omega sub 1 is the first uncountable ordinal. Or I guess I should say the least. One more kind of thing I want to introduce before I take a pause. A pretty interesting property of the ordinal numbers is a countable union of countable ordinals is countable. And I will write that down in red. A countable union of countable ordinals is countable. And so what I mean by that is, let's say, for example, I wanted to take all the ordinals before omega plus omega, right? And I wanted to join them up in a big group. I wanted to add them all together and kind of take their conjoined size. That would still be countable. I've counted many of these guys. They're kind of indexed by the natural numbers. They're all countably infinite, but their collection is still countably infinite. Are we okay on that? That's kind of probably the biggest thing here I'm going to leave unjustified, just because it would take some time. But what we actually get with the implication of omega 1 being on top, omega 1 is the set of all countable ordinals, and so that implies that there are uncountable countable ordinals, but I'm getting into the weeds here. Okay, so I'm going to pause for a moment and open up to questions. We're still going to talk about gambling, I promise. Okay, and I'm not going to take that from you, but are we okay with everything I have written down so far? So I know that was a lot. Okay. And so remember, I'm just, the whole thing I'm trying to lead up to here is I want to justify to you just how large this ordinal is, just how far out there it is. The amount of space between, this isn't really an object, but whatever comes here and whatever comes here is so much more massive than you can even imagine. One thing to sidetrack before I get into the meat of this talk. You might be asking, okay, I said omega 1 is the least uncountable ordinal, and I said that this guy is uncountable, okay? Be careful, and I'm gonna open Pandora's box and then immediately close it again with my statement. We do not necessarily know that the cardinality of this guy equals omega 1. This is actually an unprovable statement. I'm not going to get into what that means, but just don't write this down if you leave this room.
You should put a big red X.
Yeah. Well, technically not an X, but I'll do this. Question mark? So do not leave this talk and be like, hey, don't go to Dr. Eisenberg and be like, hey, Roman told me that the cardinality of the reals is omega 1. He will disown me as a student. Right?
See, I was about to go do that.
I know, right? But anyway, so I want to try and justify just how large this line is. Okay, there's a lot going on this board. I'm going to erase some of it. I'm gonna try and do my slot machine work before Omega, because I think it's kind of nice to have this picture of, you know, infinity starts here and keeps going. I think it's kind of nice to have in context. So, all right, here is our casino, right? I'll even do it in color, just to be fun, just to differentiate, right? Okay, so we'll call this, and this is my clever name, Cantor's, is that an apostrophe? No. Cantor's Casino. All right, famous competition, all right? And I'll draw you a little slot machine here. So,
You should build one for all.
I know, I should have came with an infinite slot machine ready to go, right? Okay. So, and we've got a little lever, and then I've got, I don't know, the money comes out here, and then you gotta pay a coin. And it only costs 1 coin to play. Whatever, not a cent, but 1 coin to play. Okay, so here are the rules of this casino, okay? So, costs 1 coin to play. So I should say 1 coin to play. Every time you pull the lever, you get back a countable quantity of coins. And so, when I say a countable quantity of coins back, it could be finite, or it could be infinite. I mean, you can really win big here. You can spend 1 coin, you can get an infinite number of coins back. I mean, this is a real good deal, all right? A real good deal. But gambling addicts be warned, it might not work out so well for you, okay? I'm gonna try and demonstrate that for you. So the overarching question is, if I'm a gambling addict, which, you know, who amongst us is not, can I reach Omega 1, if I keep pulling that lever, can I reach Omega 1 and make a profit? And so let's explore that for a moment here. Okay, so I'm going to define a couple of things, and I tried to pick out symbols that I thought were very user-friendly, because when I researched this online, they liked using the very complex letters. Okay, what do I say? Alright, so we typically use Greek letters to denote ordinals. So at stage alpha, so this could be a finite stage, this could be infinite, right? Like alpha could be right here or something. At stage alpha, I'm gonna have some amount of coins in my wallet, right? That's a pretty agreeable statement. So I'm gonna call that C sub alpha. So coins at stage alpha. And if I want to keep playing, I think we can all agree that there's some subset of the coins I currently have that will need to be played at some point, right? I think that's pretty agreeable. If I want to keep going, I can try and save some winnings, right? If I want to do a strategy, I can save some winnings, but some of my wallet needs to be used to keep playing. Okay, so I'm going to introduce this new function symbol, and I'm going to call it S alpha. And what S alpha is going to tell me is that when I'm at a stage and I have coins in my wallet, if I'm going to keep playing, at some point I will have spent the last coin I obtained on stage C alpha, right? So if I'm at stage, I'll keep it finite, at stage 1,000,000, okay? Let's say I have 1,000,000 coins in my pocket, and I'm going to want to spend at least 500,000 of them. There's a last time I'm ever going to spend a coin that I earn in that 500,000. There's a last time that occurs. So S alpha is the last time a coin earned at stage C alpha, well, I guess just stage alpha, is ever played. So S alpha is the last time I ever play a coin earned at stage alpha. And now I do need to make a little bit of space here, so this guy's gonna go. All right, good so far? I have my bank, and I have the last time that we're gonna see something from that bank. And we're gonna create a sequence using this concept, all right? And I'm gonna do some recursion here, so don't get too scared, right? Don't run away on me. Are you the CS major in here? Right? So you'll love recursion, right? That's up your alley. Okay, so I'm gonna make this new sequence. I'm gonna call it L to stand for last stage. This is just my, oops, sorry. This is just my naming convention. All right. So L sub 0 is going to be equal to 1. So I'm starting all the way at the bottom. My rule in general is that for L of n plus 1, this is going to be equal to S of L sub n. I'm going to explain this, don't worry. Don't freak out. Okay. So let's explore what this means for a moment. At stage L0, I'm at 1. So I know I erased all my natural numbers, but I'm starting all the way at the bottom of the list. Okay. L sub 1, following my rule, well, 1 is 0 plus 1, so this is going to be equal to S sub L0, and this is equal, well, L0 is equal to 1, so that's S of 1, okay? And what does S of 1 mean? S of 1 tells me the last stage, again, I erased my natural numbers. S1 is the last stage at which I will ever play a coin earned from stage 1. So on that first time I put a coin in the machine, let's say I get real lucky and I get omega coins back, I get an infinite number of coins back. S1 tells me the last time I ever play a coin, and that's what L1 tells me. So kind of, I start at a point and I jump to the last time I can ever play a coin. All right, I'll do another one just for example. L2 is S sub L1, which is equal to S sub 1. So again, I'm starting at 1. Let's say I strike lucky, I jump to an infinite stage, I get infinitely many coins. Or sorry, I should say, I'm at stage 1, I earned infinitely many coins. There's a point at which I play the last coin earned. Let's say that lands me right here. L2 says, all right, by the time I reach this point, I'm gonna earn more coins, right? I'm still playing, I'm still earning. When's the last time I play a coin from that time? And it jumps me even further. So I get this increasing sequence. So I could imagine like, you know, L0 is down here. Let's say I get lucky, I get L1. I earn, I can keep playing all the way until L2. I earn and earn and earn, I can keep playing until L3, and so on and so on. So you kind of get this mental image of playing as far as possible. L kind of imagines how far can I go. If I'm greedy as possible, how far can I go? All right. Now here's the real kicker. I'm going to define big L as the supremum of L sub n. And so, if you don't know what supremum means, that's okay. In ordinals, this works out really nicely. This is simply the union of all L sub n. So all I'm essentially doing here with big L is I have this sequence, L1, L2, L3, L4. It's going to keep jumping up and jumping up and jumping up and jumping up. L is going to be the collection of all of those. So it's like the kind of like the last time I can ever play, right? The last time I ever play. Are we okay on this idea? Right, that's important. Okay. Now let me ask you a question. Is L countable? There's something written on the board that should help you, Hazel.
You have a countable union
I do.
of countable ordinals.
I do.
Is countable.
I do. So L is countable, right? Every single one of these guys is countable. I'm taking a countable union, all the natural numbers. And so this guy is countable. Okay, so here's the big question. I want to keep pulling this lever all the way until omega 1. And I know my big L is somewhere out here, strictly before omega 1. And I want to ask myself, when I reach stage L, can I keep playing? And I'll use, I guess, even a different color, just kind of send the point home, right? Okay, so, I'll go over here, I'm still in frame. Let's imagine that at stage L, I have at least one coin left, right? I'm gonna be very fickle, okay? One coin left. At least one coin. Okay. If I have a coin at stage L, can you agree with me that I had to have earned that coin at some point? It's not a crazy idea, right? You had to get the coin somewhere. It had to show up somewhere. Well, this coin at stage L, I had to have earned it somewhere. At some point in my sequence, I had to earn it, either at or before stage L sub n. Okay, but get this. Is L a successor or a limit ordinal? Hazel?
Because of the way we've defined L, and we have that really fun L sub n plus one, right? We can tell that L is not a limit, it's a successor here, I believe.
Actually, the other way around.
Oh, no.
L is a limit, and I guess maybe I should have been a bit more careful in justifying that. But because I'm taking L as the supremum of all LNs, if I have Ln existing, and I have Ln plus 1 existing, those both get soaked up from omega, and so L is a limit, right? And so what this means is that if I had a coin at or before stage Ln, we know this is true, okay? When's the last time I could ever play a coin earned before Ln?
L.
Not L,
Oh.
be even more specific. How did I define my L sequence? The last stage. Yeah, say it again? Ln plus 1. Yeah. So I have a coin at or before stage Ln. The last time that coin gets played is Ln plus 1. And what does this imply? Well, Ln is less than Ln plus 1 is less than L because of the limit. So in fact, I have no coin at the stage L. Right? I assume that coin existed, but I had to get it from somewhere, and if I got it from a stage at Ln, I've already spent it before I even reach L. And so in fact, if the gambling addict plays the infinite slot machine, you will always go bankrupt. There's no way to make infinite money off the infinite slot machine. You will always run out of money before you ever reach omega 1. And so that's essentially it, right? Just to wrap up, what I'm trying to convince you of is, even if you're making infinite money for an infinite number of plays, I'm getting free money all the time. The ordinals are such a large collection that you can still run out before you even touch the smallest accountable ordinal. And you know, if that really shocks you to your core, don't worry, omega 1 is small. We still have omega 2, we have omega 3, we have omega, we have omega, right, it goes on forever. But anyway, that's it for the talk. Thank you for that. Any questions? I know I'm dying of heat right now, but. Hey, sure, all right, I'll see you later. Any questions? What'd you think for my first time giving a talk like this? I'm used to teaching pre-calc. This is set theory, so it's a step up for me. All right, well, thank you for attending. Hopefully you will consider coming to Math Club in the future. All right, that's all I got for you guys. Thank you.
That was awesome.
Thank you, Hazel.
Well,
I'm